Good afternoon, class. We are looking at Chapter 8, Further Applications of Trigonometric Functions, Section 8.6, Vectors. So, in this section, the objectives are graph vectors, find a position vector, add and subtract vectors algebraically, find the scalar multiple and the magnitude of a vector, find a unit vector, find a vector from its direction and magnitude. Model with vectors, find the dot product of two vectors, find the angle between two vectors, determine whether two vectors are parallel or orthogonal, decompose a vector into two orthogonal vectors, compute work. So reminding you of polar coordinates, you have a rectangular grid X and Y and a point P has coordinates X comma Y. It can also have coordinates R comma theta, which becomes a polar format. And this is the X-axis, which becomes a polar axis. This is the origin that becomes a pole. In the case of a rectangular, we have X comma Y, polar we have R comma theta, X squared plus Y squared equals R squared. Tan theta is Y over X, and we adjust for quadrant. In the case of a polar, we have R comma theta to take it to rectangular format X comma Y. We use the fact that X is R cosine theta and Y equals R sine theta. Polar coordinates are not unique, can be represented as R comma theta or R comma theta plus 2k pi, a complete revolution, add as many as you want. If you want R to be negative, minus R theta plus pi plus 2k pi, where k is an integer. This means odd multiples of pi, whereas this one means even multiples of pi. So a rectangular grid, okay, for example, 1 comma 2, 1 to the right, 2 up, negative 3 comma 1, 3 to the left, 1 up. When it comes to a polar, first and foremost, you locate the angle theta, meaning this is 0, this is pi over 180, this is pi over 2, this is 3 pi over 2, of course, pi over 2 or 90 or 3 pi over 2 or 270. So in the case of 2 comma pi over 4, first you locate pi over 4. The way it works, you can go with circle centered at 0, 0, concentric, circles. The circle with radius 1, then radius 2, and so forth. So you go with 1 and 2 tick marks. That means the second circle. 4 and 5 pi over 4, you locate the angle 5 pi over 4, and you go 4 tick marks, the fourth circle. And of course, more here. Finally, pole has coordinates R comma theta, and it's 0 comma theta. In other words, there are infinitely many ways of representing a pole. As long as R is 0, theta can be any number. Now, reminding you of complex plane de Moivre's theorem, a complex number z equals x plus yi. And right here, I want to remind you, a plus bi is the same thing. X and y are real numbers. I, by definition, is square root of negative 1. So if I square root of negative 1, I squared is minus 1, I cubed is minus I to the power of 4 is 1. The magnitude, also known as modulus of z, is the distance from the origin to the point x comma y, which is equal to square root of x squared plus y squared, or r. Z is x plus yi, and its complex conjugate, a plus bi, becomes a minus bi, so z bar becomes x minus yi. And the modulus or the magnitude, or r, is square root of x squared plus y squared, or square root of z bar, the product of the two under the radical. And recall that a plus bi and a minus bi, when we multiply, and becomes a squared plus b squared. Okay. So x is r cosine theta, y is r sine theta, r is positive, theta is between 0 and 2 pi. Complex numbers, x plus yi can be represented in the polar format r cis theta or r cosine theta plus I r sine theta. This is the complex plane. The x-axis is the real axis, the y-axis is the imaginary axis. So r is r cis theta or r e to the power of theta. R squared is x squared plus y squared. Tan theta is y over x. A lot of repeat stuff here. So if you happen to have two complex numbers, z1 and z2, when we multiply, z1, z2 becomes r1, r2, and then you add up their arguments, cosine of cis theta 1 plus theta 2. Again, I like to go with this format. It's a shorthand notation. Cis means cosine of something and then I sine of something. And if you're dividing the shorthand notation, z1 over z2 is r1 over r2 cis theta 1 minus theta 2. And the Moir's theorem, in essence, expansion of the concept of multiplication, z to the power of n is r to the power of n, and you multiply the theta by n cosine n theta plus I sine n theta, or z to the power of n is r to the power of n cis n theta. If you want to take a root where w, some number, complex number, is represented as r cis theta sub 0, and n is larger than or equal to 2, there are n distinct complex roots of w, the nth root of r, cis theta sub 0 over n plus 2k power over n, and k is either 0, 1, 2, all the way to n minus 1, and 2k pi over n, or 360 degrees k over n. Depends whether we go with the degree format or the radian format. Now, new stuff, 8.8, vectors, geometric vectors, and scalars. Vector is a quantity that has both magnitude and direction. Scalar is a quantity that has magnitude only. Examples: weight versus mass, velocity versus speed. Vector, scalar. Vector, scalar. So we have a line that contains 2 points P and Q. We have a line segment, a portion of that PQ. And now we have a directed line, PQ, and we have the initial point and a terminal point, and that's a vector. So given vector PQ, sometimes we just write PQ and we put the arrow at top of it. The magnitude is distance from P to Q. So the distance. Direction is from P to Q. So look at the arrow. PQ, RS, TU. Now, two vectors are equal. V equals PQ, V equals W, if they have the same magnitude and direction. It doesn't matter where you have them, as long as they have the same direction. That means they are parallel, and same direction means, they are parallel and they are pointing towards the same side. So magnitude and direction. Properties, vector properties of addition and scalar products. Vector addition is commutative and associative. Vectors are V and W. Scalars are real numbers, for example, alpha and beta. So if you add them up, you can add them up in any order. This is commutative property. V plus W or W plus V makes no difference. Associative property, U plus V plus W, do it in any order. That's the meaning of associative property. V plus 0 is the same as 0 plus V, and we get the V back. And V plus its opposite minus V is equal to 0. So a lot of properties that the addition property has works out here. Definition of a difference. V minus W, that means V plus minus W, which is the opposite of W. That's the idea. So properties of scalar products. multiplying vectors by number geometrically or scalar, what happens to them? If I multiply it by 0, of course, it becomes 0. If I multiply it by 1, I get the same vector. If I multiply it by -1, minus v means the opposite direction, same magnitude, opposite direction as v. Alpha plus beta times v, I can say alpha v plus beta times v. Alpha is a number, is a scalar. Alpha times v plus w, we distribute. Alpha times beta times v, it's alpha beta times v. It's an associative property of the multiplication. And take a look, this is v. Now, if we have the same direction, but the size, the magnitude is 2 times, is 2v, it doesn't matter where it begins. And if it has the same size, but it's in the opposite direction, it's minus v or minus 1v. It means the same thing. So, adding vectors geometrically, v and w. The initial point of v is here. The terminal point of v is here. And this is the initial point of w, terminal point of w. And you connect the initial point of v to the terminal point of w. That's how you add them. V plus w. This is v plus w, which is, of course, the same as w plus v. Notice this is parallel to this, same size, so they are identical. This one is parallel to this, same side, they are identical. So commutative property says I can put them in any order. V plus w, w plus v makes no difference. Associative property says if I have 3 of them, I can add them in any order. U plus v plus w is u plus v plus w. So if we look at this, this is u, this is v, this is w. So we can say this is uv, this is w, and the red one is u plus v plus w, or I can say u, I'm going to add v and w, okay, and I get v plus w, and then add them up in any order. The answer is what you see. Therefore, u plus v, that's it, plus w results in their sum. Or this is u, and then v plus w. And we get the answer. All right. Opposite vectors, v and its opposite, minus v, they add up to 0 vector. This 0 is a 0 vector. So v and minus v. 0 vector, v plus 0 is 0 plus v is equal to v. The difference, v minus w, is v plus the opposite. So how do we do that? Here's v, here's w. Okay. So this would be v plus w. You can put the w here and add them up. Okay. But if you want v minus w, you connect the terminal point of w to terminal point of v, v minus w, because this is the same as minus w. And v minus w is from the terminal point of w to terminal point of v. In other words, so this is v. Remember, if this is v, so is this one, right? The two are parallel, same size, they are identical. If this is w, everybody, this is minus w, right? So just look at the green ones. That gives you u minus w. So or either that, or just remember, V minus W would be the terminal point of W to terminal point of V. Whatever that makes it easier. Either way, that would be the answer. All right. Now let's take a look at a couple of examples of that. V is given, W is given, U is given, and we want to get V minus W. Here's V. Here's W. So put it right here. And because it's minus, going in opposite direction. So again, here's W, parallel to that, and going in the opposite direction. Makes it minus W. And then connect them. So it looks like that. Two V. So look at V and just continue and same direction and make the size 2 times. So that's 2V. This is W. Same direction, make it 3 times. And connect them. Now, 2V, we already have it here. Minus W is this, so let's put it here, right? They are parallel. It's important to understand that as long as you have the parallel, it's the same thing. So put this one here and call it minus W. And then you put it here, parallel, right? This one, parallel is here. So that's the same. This is U. So 2V, everybody, 2V minus W plus U. Connect them. Connect this point to this point. This is what you get. Magnitude of vectors. And here's the notation. This is the magnitude notation. Looks like an absolute value, but two line segments. To compute the magnitude and direction of a vector, an algebraic way of representing vectors is needed. Position vector. If the vector with components A, B is an algebraic vector whose initial point is at the origin, then V is called a position vector. In other words, remember, two vectors that are parallel and they are having the same magnitude, they have the same direction, they're identical. It doesn't matter where in space. So if you move them such that the initial point is at the origin, it's called the position vector. That's all. Algebraic vectors, V is AI plus BJ, or just AB. A and B are called components of the vector V. Magnitude of a vector is square root of A squared plus B squared. Magnitude is always non-negative, it's greater than or equal to 0. Two vectors that are opposite, they have the same magnitude. Okay. If the magnitude is 0, the vector must be 0. And if you multiply by A, you can take it out. Unit vector is a vector whose magnitude is 1 by definition, everybody. A vector with initial and terminal points x sub 1 and y sub 1 and q x sub 2 and y sub 2 is equal to the position vector v equals pq x sub 2 minus x sub 1 comma y sub 2 minus y sub 1. That's how you get there. Or position vector v for p1, p2 has components a, b, x sub 2 minus x sub 1 comma y sub 2 minus y sub 1. Angle brackets, sometimes known as chevrons, are used to represent vectors. So I just wanted to mention this this notation is called angle brackets, also called chevrons. Just in case if anybody is interested to know about that. Well, if we look at this one, and the initial point at x sub 1, y sub 1, terminal point at x sub 2 minus comma y sub 2. This distance along the x-axis is x sub 2 minus x sub 1. Along the y-axis is y sub 2 minus y sub 1. And if you move that such that the initial value is at 0, 0, it becomes a position function. So I hope everybody's fine with that. So let's find the position vector of the vector v equals p1, p2, where p1 is negative 1, 2, and p2 is 4, comma 6. Well, all we have to do, just follow the formula, which is x sub 2 minus x sub 1, y sub 2 minus y sub 1. Okay, so first of all, this is the given. You just pinpoint negative 1, 2, and 4, 6, you connect them. This is the given vector, everybody. Following the formula, x sub 2 minus x sub 1. 4 minus negative 1. So it's important to know that the terminal point minus the initial point, the x coordinates, 4 minus minus 1. And for the y, 6 minus 2. This is plus 1 makes it 5. This is minus 2 makes it 4. So it's the same as 5 comma 4. So you go 5 units to the right, 4 units up, 5 units to the right, 4 units up. These two are in essence identical. The difference is this is called a position vector because the initial point is at 0, 0. Vector equality. That's the theorem we're going to discuss. Two vectors are equal if their corresponding components are equal. For example, V has components A1, B1, W has components A2, B2. If A1 and A2 are equal and B1 and B2 are equal, the two are identical. So unit vector is a vector u such that the magnitude of that equals 1. Now, unit vector I and j, this is along the x-axis 1, 0. This is along the y-axis 0, 1. And with that being the case, a vector AB can be A times the unit vector along the x-axis 1, 0 plus B times the unit vector along the j-axis, the y-axis. So this becomes AI and this becomes BJ. So these are various formats of representing a vector. Now find the position vector V equals PQ if P is given and Q is given. Well, basically x sub 2 minus x sub 1, y sub 2 minus y sub 1. So for the position vector, we get 4 minus 4, 6 minus 9, according to this formula. So this becomes 0. This becomes negative 3. And we're done. It also means 0i minus 3j. So just minus 3j. That is the same as what we just mentioned. Find a vector from its direction and magnitude. A vector with components AB, unit vector. This is something we know already. Unit vector in the direction of V is equal to V divided by its magnitude. Find a vector from its direction and magnitude. Any vector, it's the product of its magnitude and cosine of alpha I plus sine of alpha j. Meaning, if you're looking at this vector, you can calculate this magnitude and you can see the alpha, which is the angle between the positive side of the x-axis and the vector. Therefore, the magnitude is square root of a squared plus b squared. The unit vector is v divided by the magnitude of that. And any vector can be the magnitude times the unit vector if you do the cross product here. So find the vector v whose magnitude is 7 and whose component in the I direction is both positive and equal to the component in the j direction. Well, the components are A and B, and A and B, we know when we square them, A squared plus B squared is the magnitude squared. So in other words, if you look at this one, if the magnitude is 7, then square root of A squared plus B squared is 7. So A squared plus B squared is 7 squared. So according to this, right? AI and BJ, A is equal to B. So that's the given part, everybody. So A squared plus B squared is 7 squared. Because they are identical, you can say A squared plus A squared. That means 2A squared. So let's change this also to A squared. 2A squared is 49. A squared is 49 divided by 2. And A equals B is the square root of this. And A is the square root of 49. over 2, which is 7 over square root of 2 times square root of 2 over square root of 2 gives us 7 square root of 2 over 2. Those are the components, everybody. So the vector is 7 square root of 2 over 2i plus 7 square root of 2 over 2j. There are different ways of representing it. That's one way to do so. Finding a unit vector has magnitude 1. Unit vector in the direction of v, u is v divided by its magnitude. Magnitude of a vector which has components a, b is square root of a squared plus b squared, and v is magnitude of v times u. We already know that. We've discussed that already. So let's look at this example. Find a unit vector in the same direction for the following vector, negative 3i plus 4j. All we have to do, step 1, find the magnitude, square root of a squared plus b squared, which is square root of minus 3 squared plus 4 squared. As you know, this is 9, 16. They add up to 25, comes out as 5. Now, we use this formula. We're going to divide the given vector minus 3i plus 4j by this number. So we get negative 3 over 5i plus 4 over 5j. And we're done. But as far as checking, everybody, if I square this number and this number, they should add up to 1. And then I take a square root is also 1. So you don't even have to take the square root. But let's add up. Negative 3 over 5 to the power of 2, as you know, it's 9 over 25. 4 over 5 to the power of 2 is 16 over 25, which makes it 1. And because it's 1, the square root is also 1. I mean, if you didn't do that, if you said this is 1, that's good enough for the proof. Okay, everyone? So let's continue finding a vector from its direction and magnitude. And again, the vector is the magnitude times cosine alpha I plus sine alpha j, which is the unit vector in the same direction. And again, the magnitude is that. And alpha is between v and I. Alpha is between 0 and 360 degrees. And so here's the example. We want to find the direction angle for v equals negative 3i plus 3j. So in essence, if you go 3 units to the left plus 3 units up, and then calculate the angle. So this is 3 units left, 3 units up. And so if you want this angle, tan of theta, is the y3 over x minus 3 or b over a in essence. So 3 over minus 3 is negative 1. And since theta is in the second quadrant, remember, negative 1, there are 2 answers, but specifically we know it's the quadrant 2. If it were positive 2, would be 45 degrees. So this one would be 180 minus 45, which makes it 135 degrees because that's the reference of. Find the vector v whose magnitude is 9 and the angle it makes with the positive x-axis is 225 degrees. Well, the magnitude is square root of a squared plus b squared equals 9. So basically this is 9. And you're going to replace the alpha with 225 degrees. So this is 9, alpha I plus AI plus bj, or the component one, or just cosine alpha I, okay? So you can put it into this, or just find the cosine, or just multiply it by the magnitude in any event. So A is 9, the magnitude, times cosine of 225 degrees. B is 9 sine of 225 degrees. Now, 225 degrees, we are looking at really the reference arc 45 degrees. We are dealing with the third quadrant. In the third quadrant, sine and cosine are both negative. Both of them are square root of 2 over 2. Both of them are negative. Both of them are minus square root of 2 over 2. Therefore, the vector is minus 9 square root of 2 over 2, I minus 9 square root of 2 over 2j. So it's pretty straightforward. Add and subtract vectors algebraically, vector properties of addition and scalar products that we are familiar with. And so the way it works, if V is A1I plus B1J or A1B1, and W is A2I plus B2J or A2B2, okay? So we're going to expand on that. V plus W, we just add up the components. The I components would be A1 plus A2 times I, and the J components would be B1 plus B2 times J, or in this form. If you want to subtract it in the same manner, V minus W would be A minus A1 minus A2I plus B1 minus B2J, and you can see the answer here also. So take a look. Here's the V, here's the W, okay. V with components A1, B1, W with the components A2, B2. When we put them here and continue, they add up, the components add up. So this is B1. For example, this is B2. This is A1. This is A2, and they do add up. Alpha times V, when you multiply it by a number, by a scale. Scalar is a number. Alpha A1I plus alpha B1J. So alpha A1 and alpha B1, meaning if you're looking at this, V, and then you multiply it by some number, it extends by that number. So we have this component A1 has been multiplied by alpha along the I direction or X direction. B1 has been multiplied by alpha along the Y or J direction. Again, magnitude of the vectors has been discussed already. And so illustration of property 5. The magnitude is distance from O to P1. The magnitude is square root of A1 squared plus B1 squared. Right, this Pythagorean theorem. Let's add and subtract vectors algebraically, everybody. V is given, W is given. We are to add them up. So if I want to add them up, I'm going to write them. And I'm going to add up the components. This one and this one, they add up to negative I. This one and this one, they add up to negative J, and we are done. V minus W works the same way. Let's distribute here and write minus 2I plus 5J. Add these two, we get negative 5I, 4J, 5J. They add up to 9J. So just add up the components. Imagine you're adding like terms. Okay, that would be an easy way to discuss that. Imagine you're adding like terms. Find the scalar multiple and the magnitude of a vector. V is given, W is given. We want 3 times V. Just write it 3 times, write the vector, and simply put, if you want to go with this format or that format, makes no difference. 3 times this one or times this one, they're identical. This gives us negative 9, this gives us 12, and we're done. 2V minus 3W, 2 times this one minus 3 times this one. Again, you can go with this format or this format, makes no difference. We're going to distribute the 2, we get minus 6 comma 8. We're going to distribute the negative 3 plus negative 6 positive 15. It's better to put them in a plus form, everybody. And so these two add up to negative 12, positive 8, positive 15. They add up to 23. So very straightforward, everybody. What about the magnitude of one of them? In this case, V square root of A squared plus B squared, or A1 squared plus B1 squared. So you add up square root of negative 3 squared and then positive 4 squared. Negative 3 and 4. Negative 3 squared is 9, 16. You get 25, comes out as 5. Resultant force, that means adding up. So F1 and F2, you add them up, you get F1 plus F2, just the way you would do vectors. And force is considered to be a vector. Here's an example. A plane is flying at a speed of 200 miles per hour on a bearing of north 55 degrees east. So this is north, this is east, so this way. Okay. The wind is blowing from west to east this way. Approximate the ground speed of the plane to the nearest mile per hour and the true course of the plane to the nearest tenth of a degree. So Let's see what's given. Let's do the drawing. I can't emphasize this enough. It's important to do that. So first and foremost, we are going in this direction, north 55 degrees east. And it doesn't have to be to scale, but that is the plane, the vector for the speed of the for the plane that compared to the to air in essence. So remember, for the vectors, we want the angle that it makes with the positive side of the x-axis. Let me just do this. Okay, and so this angle must be 90 minus 55 or 35 degrees. That's the first thing I want everybody to recognize that. So this velocity relative to air, VA, is 200 miles per hour. That's the magnitude. And the angle is 35 degrees, 90 minus 55. And now the wind is blowing at 35 miles per hour from west to east, this way. Now the wind, the magnitude is 35 miles per hour, and the angle it makes, this is parallel to the x-axis. So the angle it makes is 0. And so we are going from here to here. When we combine the two, that is the resultant force. Okay, everyone? And this resultant force, it has a magnitude we have to figure out, and it has an angle that it makes with the positive side of the x-axis. We're going to call it theta. So the ground speed would be the magnitude miles per hour, and the angle would be 90 minus the green one, which is theta. So 90 minus theta, okay? The true course, my apologies. The true course is this angle, 90 minus theta. And of course, it is still north, that angle east. So let's write this 2 in this format, everybody. The magnitude times cosine alpha I plus sine alpha j, in this case, would be 200 cosine of 35 degrees I sine of 35 degrees j. It's not a common arc. You put it into a calculator, you find cosine of 35 times 200. Same thing with sine of 35 times 200. And it ends up being this. You put a couple of decimals. As far as the number of decimals, you really should carry as many as they want. Normally, many decimals. So it becomes 163.83i plus 114.72j. Now we do the same thing with the wind, and it's 35 cosine of 0 degrees sine of 0 degrees. Cosine of 0 degrees times I, sine of 0 degrees times j, and as you know, sine is 0, cosine is 1, so simply put 35i. And the resultant would be the sum of the two vectors, and the way you add them, you add up the components. So you add up these two, and the second part remains of 114.72 because it doesn't have a component, because this is plus, in essence, 0j. So we get 198.83 I plus 114.72 j. So now all we have to do, come up with the magnitude, everybody. Square root of a squared plus b squared. which means we're going to plug in this number and square it. We're going to plug in this number and square it, add them up, put it into a calculator, and you end up with 230 miles per hour, which means true course is northeast, and the magnitude is 230 miles per hour. We need to find the theta to subtract it from 90. And tan of theta, or in this case, alpha, if you want, is B over A. So B over 114.72 divided by 198.83, and that becomes about 30 degrees. So the speed is 230 miles per hour. Direction north, 90 minus 30, that means north 60 degrees east. A quick recap, everybody. So a plane is flying at 200 miles per hour on a bearing of north 55 degrees east. We can calculate then this angle to be 35 degrees, and we write it in this fashion. The wind from west to east, we can write it in this fashion, becomes 35R. We add components. Using the components squared, we can find their magnitude. The true course is northeast. We have to find this angle. To find this angle, we find the angle between the true course and the positive side of the x-axis subtracted from 90 degrees. That's how we arrive at the answer. So that's how vector is used, application in mostly physics. A box, so an object in static equilibrium, a box that weighs 1,200 pounds is suspended by two cables as shown. Find the tension, the magnitude in each cable. Okay, so first we're going to go with a free body diagram, which looks like this. So this is the weight towards the center of the gravity, center of the air. This is 30 degrees, so is this one. This is the tension F1. This is 45 degrees. And 45 degrees this way, it's F2. And what you're looking at is the body diagram. So what is that? A free body diagram show two or more forces acting on an object body if the object is in an equilibrium state, meaning all forces must add up to zero. That means the forces along the x-axis, along the y-axis, each one is zero. All forces add up to zero if it's an equilibrium state. So let's look at F1. As far as the angle, if this is 30, everybody, this is 150. Okay. So we are going to go with this format, the magnitude, and that's what we are looking for, by the way. So the magnitude of F1 and cosine of alpha, which is 150 degrees, I sine of alpha, the same thing, sine of 150 degrees, J. So that would be F1. Okay. This is F1. This is the magnitude of F1. What about F2? F2 is the magnitude of F2 and then cosine of this angle, 45 degrees I plus sine of 45 degrees J. And what about F3? The magnitude of F3 is given as 1,200 pounds, everybody. That is the magnitude. The direction is going down. So the angle that it makes is 90 degrees in the negative direction, minus 90 degrees. So it's minus 1200 J. So the magnitude is 1200 pounds. F3 is minus 1200 J. Or just put it in cosine of minus 90 degrees I, sine of minus 90 degrees J. Cosine is 0, sine is negative 1. That's how you get negative 1200. Now, this is extremely important. What this means is the following. Summation of F is 0. All forces must add up to 0. That means all forces, summation of F sub I along the I and along the J, along the X and along the Y must also be 0. So if you want to write this, you're going to write F1 plus F2 plus F3 equal to 0. So let's find what's F1, F2, and F3. Well, we have the F3. We are in good shape. Let's find those 150 degrees. Remember, the reference arc is 30 degrees. And so this is cosine of 30 degrees, which is square root of 3 over 2 in the second quadrant negative. This is sine of 30 degrees in the second quadrant, sine is positive. So this is minus square root of 3 over 2, but this is positive 1/2. 45 degrees, both of them are square root of 2 over 2. So this is negative square root of 3 over 2, 1/2. This is both of them square root of 2 over 2. So F1 would be, if we multiply, because we want to add up the components, the magnitude of F1 times minus square root of 3 over 2 times I, magnitude of F1 times 1/2 times J, this one magnitude of F2 times square root of 2 over 2 I, and J. And this one is minus 1200 J. So let's write all of them. So again, look at just the first one. Minus square root of 3 over 2 times magnitude of F1I. This one is 1/2 magnitude of F1J, and the rest of them fall. Now, the I components are these two, and they must add up to 0. So write these two here. They must add up to 0. The rest of them are J components. They must also add up to 0. So write them here. So make them big enough so everybody can see that. Now, this is the system. I hope you recognize this as a system of equations with two variables, magnitude of F1 and F2. And I'm going to solve it in the next page. I'm going to show you how we solve that. When we go through the process, magnitude of F1 becomes precisely 2400 over square root of 3 plus 1, roughly 878.5 pounds. And magnitude of F2 becomes square root of 3 over square root of 2, 2400 over square root of 3 plus 1. Put into a calculator, roughly 1075.9 pounds. Okay, so the point being, of course, we are going to look at it in the next page, but that's how you arrive at the answer going through the system of equations, everybody. So it means this is going down by 1200 pounds. This F1 is going this way, 878.5 pounds, and this is going this way, 1075.9 pounds. These two can cancel these two along the X and Y direction, and that's an equilibrium state. All right, let's look at how we solve that. So I'm going to quickly go back and show you this is what I'm going to rewrite. So this is the system I'm going to rewrite here. And to solve that, I'm going to do it in a couple of steps. First of all, we don't like fractions. Let's multiply both of them by 2. So that's the first thing we are going to do. When I multiply this by 2, the denominators 2 and 2 and 2 and 2, both of them go away. So the first one becomes minus square root of 3 absolute magnitude of f1 plus square root of 2 magnitude of f2 equals 0. And the second one, 1/2 goes away and becomes magnitude of f1. The second one, the denominator goes away, square root of 2 magnitude of f2, and minus 1200, everybody. I move it to the other side, becomes 1200 times 2. So this is 2 times 1200. I want to make sure everybody understands how we arrive at. So when you multiply this one by 2, you get minus 2400. You move it to the other side. So what is our next step? Let me erase my work. I need that space. What is the next step? You see these two are identical. You can say I'm going to subtract one from the other one. Or you can say, okay, let me multiply this one or this one, doesn't matter. This one by -1. If I multiply this one by -1, this doesn't change. This becomes positive, this becomes negative. Now, if I add them up, these two cancel each other. So these two add up to square root of 3 plus, this has a coefficient 1, square root of 3 plus 1, magnitude of f1, these two add up to 2400. Therefore, magnitude of f1 is 2400 by square root of 3 plus 1. That's what we had in the previous page. Exact answer, roughly 878.5 pounds. I hope everybody's okay with that so far. It's simply the method of solving a system of equations. It's really not a big deal, everybody. And now we use one of the equations, and you should always use one of the original equations. For example, if we use the first one. I hope you see that you can solve for this. You can you take this one to the other side, becomes positive. The 2's cancel out, and square root of 3 over square root of 2. So I hope you recognize the easy algebra here. So the magnitude of f2 is square root of 3 over square root of 2 times magnitude of f1. So multiply this number by this number exactly. Now you put it into a calculator and you get 1075.9 pounds. So I just wanted to show you how the system of equations is solved here, because it's a little bit involved.